What I'm going to talk about today is functional programming for data science, or at least that's the title of the talk. It's one I've given a couple of times, and it's sort of evolved as I've done it. It started off relying quite heavily on Scala and talking about functional programming kind of in a very data sciencey type context. This being Pycon, I decided to change it around a little bit, and it's more sort of Python heavy than it has been in the past. So maybe you could say there's a little more emphasis on the first two words of the title than on the last two. It's going to be more kind of functional programming heavy with an emphasis on how to implement kind of functional ideas in Python and what you benefit by, or how you benefit from doing that. So I guess I'll begin just by introducing myself. Oh, I've gotten suddenly much louder. Can you hear me okay now? Yeah. Oh, great, okay. Could anyone hear the first set of things I said? Or was that just for me? So. All right, fair enough. Well, I'm going to talk about functional programming effectively, all right? So I'll begin just by introducing myself. My name is Neal. I look like this on the internet, and I look like this in reality. I used to be an astrophysicist, so I did my PhD in astrophysics just down the road here in Trinity College. Worked in the field for a little while doing research, kind of doing probabilistic type stuff on astrophysical data. I'm currently a data scientist, so I've left the field about 2 or 3 years ago, moved over to the UK. Based in London at the moment, where I work as a data scientist at Amazon doing lots of fun kind of machine learning stuff. And I'm going to tentatively describe myself as a functional programmer, someone who's done quite a bit of functional programming down the years, hacked quite a lot of Haskell and done quite a lot of Lisp-related stuff as well, and Clojure and other languages. But I'd like to kind of temper that by saying I'm quite a pragmatic functional programmer. I'm not going to stand up here and kind of lecture you all about monads or functors for the next 45 minutes. I want to kind of get to something practical and something useful and kind of convey some sense of how you can use functional ideas to do kind of actionable things that are relatively simple but that make your code better and cleaner. I'll temper that tempering by saying that I would say I'm a semi-pragmatic functional programmer. Anyone who was at the conference last year would have seen a talk I gave on making a Lisp in the Irish language, which is not a particularly pragmatic or practical thing to do, but it's a very functional programming kind of thing to do. So I'm ticking a couple of those boxes at least. I'll give you a brief outline of what I'm going to talk about. I'm going to talk about functional programming in a very general sense to begin with, as sort of a design philosophy and why it's valuable. I'm then going to kind of give you some reasons for why it's a useful thing to do, why you should kind of consider having using a functional paradigm in your workflow. And then I want to talk through some of the primitives in Python. So Python is not a functional language by any stretch of the imagination, and it's very heavily object-oriented. But it does provide some kind of functional primitives so that you do useful functional programming stuff in the language and gain the power of that paradigm through that. And I'll finish with a brief example, which is sort of the only really data-focused aspect of the talk. I'm going to kind of talk you through a data workflow and how you can do data stuff using this kind of functional paradigm and how hopefully it cleans up code a little bit. So let's begin just with a very kind of basic question, I guess. What is functional programming? So maybe I'll take the kind of feel for the room at the moment and get an idea of what people's background is. So have I got a lot of people in the room who are kind of very into functional programming? Guys who are like wake up in the morning thinking about monads, really into Haskell. Anyone? No, that's actually quite good. That's pretty healthy. And do I have very many people in the room who are kind of functional programming novices, wouldn't have particular knowledge, or a couple of people. Okay, so and then a lot of people who are very non-committal or afraid to venture their level of functional programming experience. That's fair enough. I think the talk is probably more aimed at people who haven't got very much experience with the paradigm to kind of demystify some of the ideas that it rests on and kind of give you some idea of why they're useful. So to go about answering this question, I'll ask a simpler one, and that question is, what is a function? Okay, so that seems like a reasonable question and a reasonable one to answer. A lot of this talk was originally motivated, funnily enough, by an academic friend of mine. So academics have a terrible reputation for writing really bad code. A huge number of people are arriving now, so maybe I'll pause while they all make their way in. Academics have a particularly terrible reputation for writing really bad code, and this friend of mine, being no exception, was talking to me about some programming practices that he's got. And one thing that he said was that he doesn't really see the value of functions, just doesn't really ever use them, doesn't think just writes it all in one long script from start to finish. And like, what do you get from using a function? He said. And amazingly, no one in the room tackled him on this. Everyone was like, well, I suppose, yeah, maybe it sort of is an optional thing. Maybe you don't really need to use a function. What is the point of a function really, Well, maybe it is more readable to just put it all in one long thing that executes from start to finish, top to bottom, right? It's very linear, right? Maybe that's a sensible thing to do. I was obviously aghast, and as a result have written this kind of diatribe about what a function is. So to address that person's question directly, a function is this. I mean, this is kind of the canonical function, right? The first function, Brian Kernighan's example in the C++ or the Introduction to C book, Hello World. So what this is well, it's an import statement at the start, which we won't worry ourselves about. And then it's an operation, so print hello world, this is an operation, embedded inside of a box effectively called main, right? We've taken this operation and we've put it inside of a compartment that we can then carry around, and we can use the operation just by calling this main function, okay? And that's kind of the motivational idea behind a function, that we can kind of structure our code such that we can compartmentalize it into little boxes, right? And carry those boxes around without having to worry too much about the implementation detail of what they're actually doing inside. Okay, we don't need to worry about how this can hello world print out to the screen. We just know that it does, right? We don't have to worry ourselves about the operations that are taking place inside of the main function. So this kind of idea of using functions this way has a very long history and goes back to kind of the first design paradigm or philosophy in programming and language design, which is called structured programming. So the idea of structured programming came around about the 50s, and kind of motivated the design of an awful lot of programming languages that were developed at the time. And the notion of structured programming is sort of so ingrained now in the way that we think about software and software design that it sort of almost goes without saying in some sense. We don't even consider it to be a paradigm. We just do things in this way. And it's kind of got two elements to it. The first is structured data. So the idea that you can structure data in lots and lots of different ways. You can have data which is in a binary search tree, an example here on the right, or you can have data which is in a linked list or a doubly linked list or a hash map or an association list. There's lots and lots of different ways that you can structure the data that you've got. And the idea in structured programming is that if you structure your data well, then you'll get a good and efficient solution to your problem, right? If you use a kind of germane structure for your data, then you'll be able to query it in a useful way, and you'll be able to put together a really good answer to the problem you're trying to address, which I think is fairly sensible, right? We'd all more or less agree with. The second idea is the one that I'm going to lay a little more emphasis on here, and that's structured code. And the notion behind structured code is really where functions kind of come into the picture when it comes to programming. And the notion is that your problem has some inherent structure to it. All problems have structure to them, or you wouldn't be able to solve it, right? It's not just a random thing, it's some structured thing that you're trying to address. And that structure kind of lends itself to being broken down into subproblems. So you can take problem and you can break it down into subproblem 1 and subproblem 2, and maybe the subproblems have subproblems inside of them, okay? And you implement each of these subproblems, address each of them in their own function, and then bring it all together in the end, and that's how you solve your problem, right? And that's fairly unimpeachable at this point. I think that's something that we all just do without thinking, right? It's just sort of the way people consider programming now. But it is a design choice. It's a design choice to break your program up in this way, or to break your solution up in this way, to address it by breaking it down into smaller, simpler subproblems, and then concatenating the answers together. And what this gets us is a whole bunch of stuff, but what it gets us primarily, and what's mostly useful to us, is modularity, right? We end up having individual compartments, individual modules of our code, which address individual subproblems, and they're really useful. Now we have this kind of Lego block type thing where we can snap together functions and put together these little modules, compose them into higher order solutions. This buys us an awful lot of stuff. So modularity is a great idea. We really like modularity. What we get from modularity is we get reusable code. So these small functions are more likely to be usable across different kinds of problem domains than if you wrote one huge monolithic function, right? If you write one big thing that solves one very specific problem, it's unlikely you're going to need to solve that exact problem again. Whereas if you write something small, then you're more likely to be portable and usable somewhere else. They're easier to code. Small functions are a good idea because it doesn't take so long to put together a small function. It's easy to see how it works. And finally, they're more debuggable, right? So the more compartmentalized and modular your program is, the more easily you'll be able to introspect it, and the more easily you'll be able to catch bugs, right? It becomes a more straightforward process to try and track those bugs down. So it's a really good idea. But it has a kind of a challenge in it, right? There's a challenge embedded in it. It's sort of summed up in one character here, and it's the plus sign in this first function, right? It's rarely going to be as easy when you break down your problem into subproblems. It's rarely going to be as simple as just adding together the answers of each of those subproblems to get the answer of the main problem, right? That's almost never the case, that you'll be able to just break down problem 1 into 2 subproblems and sum up the answers at the end, and that's the answer to the main thing, right? You need some kind of more flexible way of combining these functions, right? And that's where functional programming enters the picture. That's what functional programming is for in some sense. Functional programming is glue, right? Functional programming is a way of taking these individual functions, these individual compartmentalized, modularized solutions, and gluing them together in a more flexible way, right? It provides you with a framework to go about doing that in a way that's kind of transparent and easy to use, and as a result, more powerful. And the kind of motivating thing, this is not a new observation that I'm making. Functional programming is glue, is sort of part of the design philosophy. John Hughes, the computer scientist, not the guy who made Ferris Bueller's Day Off, wrote a really good paper on this exact topic, on the idea of functional programming as a glue for sticking together smaller programs, right, and smaller functions. And the notion that kind of motivates the whole thing, I guess, is that composability is better than complexity. So languages can get more bloated. We think of C++, or we think of Java, we think of these languages that have got really powerful tools of abstraction in them, right? Object-oriented programming languages that have, multiple dispatch and polymorphism and lots of really complicated inheritance systems and all this stuff. We get more and more powerful individual objects, more and more powerful pieces. But the idea of functional programming is that you don't need powerful pieces. What you need is simple pieces and a really flexible way of being able to compose those simple pieces together into answers, right? So this is all very kind of philosophical, kind of motivating the idea of what we're trying to do here with functional programming. So I've kind of given you an idea of what I'm driving at. What I'm driving at is a notion of, as I say, modularization and composability. That being the core of functional programming. And in my opinion, there are kind of 4 ways that functional programming provides you with this glue. There's purity, static analysis, laziness, and higher order functions. So each one of these things I'm going to talk through in the next section one by one and kind of give examples of how you can do these things in Python. Because ultimately, this being Pycon, that's what I want to impart, useful ways to go about implementing these good ideas in a language that we're all very familiar with, despite, as I say, that language not really being a functional language. So let's jump right in with the first one, and let's talk about functional programming in Python by beginning with purity. Okay, so what is purity? Purity might be something that you've come across before in discussions around functional programming. It's sort of the core concept in some respects of functional programming, or one of the core concepts in it that people talk about an awful lot. And the idea is that you want to write code that has certain properties. So this is a bad example of a not pure function, right? And it's maybe easier to talk about purity in terms of examples of purity and impurity than it is to kind of talk about it in purely abstract terms. But this is not pure because this relies on some external state that is not handed into it, okay? This function, the behavior of this function is determined by what that flag true is set to, okay? And we don't get that flag true passed in when we run the function. It's not one of the arguments of the function. So we need to know the setting of that flag to know what this function is going to do. It'll either divide our output by 10 or multiply it by 10, and we don't know what it's going to do just when we run it. We need to know what this thing is doing somewhere else in the code that could be conceptually very far away or could be being interfered with by other functions. This is an example of impurity. So the notion of purity here is kind of tied up in a function only relying on its arguments. Okay, all it does is take in arguments and return outputs. The outputs are entirely specified by the arguments. There's no internal state to the function, and there's no external state that modifies what the function is doing. Right? That's the notion behind purity here. Here's another example of a not pure function. So this is going off and reading a file and printing out the contents of that file. Takes in an argument, prints out the argument and the contents of some file called test. And this is not pure either because, of course, this test file can change at any time. Right? Someone else can go edit this file, or some other piece of code can go edit this file. There could be a race condition where this file is being overwritten somewhere else or rewritten by some other function, and we end up in a situation where this code can give really weird bugs now. Right? This thing that just looks like it's something very simple can actually do some bad stuff, right? If this file gets erased by some other function before this function gets to read it, then you're in trouble, okay? And here's another example of a kind of perniciously not pure function. This is something that maybe someone would do if they were slightly less than familiar with the way Python operates or its interface. But this scale function here is very straightforward. It takes in some data, right? It takes in a list. It iterates through the items in the list and it scales them by some value. It's kind of impure in 2 ways here. It's impure because it doesn't take in that value n as an input, okay? So it doesn't know what n is. We don't know what n is when we hand in the arguments. N is set somewhere else, as with the true example before. But this is also impure in another way that's more troubling, and that is that it mutates its input data, right? So after having run this function, both the original data and the output are the same thing, because it goes through and actually alters the list that's handed into it. Okay, so this can be a way to introduce some really pernicious. This is a very simple and transparent example. I don't think anyone would actually make this mistake in production code, but this is a place where you can get some really pernicious bugs, right? When you start mutating the state of data. So this is another idea in functional programming, that data should be immutable. You shouldn't go about changing the state of data. You should go about creating new variables based on the data that you've got. So that's the notion of purity, kind of in a nutshell. We can of course write a pure version of this function very easily using Python's list comprehension syntax. So that's an example of a pure version of this function. It takes in the list, it takes in the scaling value, it returns the list scaled and doesn't affect its input data. So a very trivial example. But now we've got a function whose behavior is only determined by its arguments and which doesn't have any other effect on the state of any variables, right? This is a good idea. This function now is more transparent, easier to debug, less likely to break and cause problems for you later on. Okay, this is what you buy from purity. So purity kind of, in that paper, that glue paper that John Hughes wrote, he says that the idea kind of functional purity sounds to some people like you're kind of a medieval monk who's denying themselves the pleasure of life because maybe they'll go to heaven. Like, don't mutate data and only take in arguments. Let your function only be determined by its arguments. Don't do anything like that. But I think you get more than just the promise of some later salvation. You also get code that is more readable, more transparent, and more less likely to break, more easy to debug. So taking that, I want to jump onto another topic which is not inherent to functional programming, but is something that is available in lots of functional languages and is kind of functional languages provide particularly powerful tools for doing this. So this is static analysis. So the notion here is that you want to be able to analyze your code without having to run it. Okay, you don't want to find bugs at runtime. You want to find bugs at the time you're writing the code or before you've had to run it. Okay, Python being a very dynamic kind of cavalier function or language doesn't really provide any functionality for doing this. Python is a dynamically typed language by design and sort of doesn't really do very much checking of anything before runtime. So it's a place where you can get a lot of breakage. So to go back to that previous example of the scaling functions, this is a very nice, let's say, pure function. We like this function. And behavior is entirely determined by its inputs. All it does is hand out outputs. It has no other effect on anything. However, that doesn't mean it's correct, right? And we can easily break this function by handing in something that it doesn't expect. So this is a bad thing, right? If you hand in these strings of 1, 2, 3, and 4, it'll scale the strings and turn them into longer strings. And that's bad behavior. You probably didn't want it to do that. You maybe hadn't thought that was a use case, but that could easily come up. Someone hasn't escaped a character before they put it into your function. And this is my least favorite kind of bug, or the worst kind of bug, where the code doesn't break, it just does something that you didn't expect it to do. And now something else will break down the line, right? Something else is going to get an input that it didn't expect. And that bug is kind of one step removed from where its source is in some sense. So this is now something that as of fairly recently, in the last 18 months to a year, is now something we can kind of deal with in Python in a way that we couldn't before. And that's as a result of Mypie. So if people aren't using Mypie, you should be. It's a wonderful tool. And Mypie is a static type checker for Python, which is developed by the guys who make Python. It's on the Python mainline repository, and it's sort of now built into the language as a 3.6 and kind of has backward compatibility to 2.7 as well. And the notion here is that you can do this kind of thing. You can import from typing, this module called typing, an object called a list. And you can define a new type called a vector, all right, which is a list of ints. All right, and then you can annotate your code here at the start with list, the inputs you're expecting here. First thing is going to be a list, and it's going to be a vector. It's going to be a list of ints. Second thing you're going to get is going to be an int, and I want you to return a vector, a list of ints for me, okay? So this is super useful. Now we are able to type check our code, right? And we're able to get some meaningful guarantees about what this code is going to do. The thing about Python, it being, as I say, dynamically typed and cavalier and all the rest, is this won't actually stop you from running bad code. You can still run the previous example that I gave, will still work with this type checking. These type checks, these type hints do nothing at runtime. They're solely just hints. But what you can do is you can check now before you run your code if these type hints are being obeyed. So if I say you can still run the code and you can still get exactly the same problem, but you can now check the code before you have to run it, and you can do that using the Mypie command line tool. So this looks like this. You just Mypie pipe in this thing called scale.py, and you get a warning every time you do a bad thing, right? So here you had 4 mistakes, 4 times you gave me a string when I wanted an int. Okay, so this is a really powerful thing, and I hope this kind of gives you an idea of a really useful workflow in Python. So you can make this part of your CI/CD system. So as you do continuous integration and continuous deployment, you can be checking, make sure that type hints are obeyed at all times. So you're not handing in weird things to functions that those functions don't expect or anticipate. This is super useful. And the way I like to think about it is that sort of by doing individual testing, so by testing individual cases of code, right, which is something we all do and we all should do, you learn about how the code performs at one point in parameter space, effectively, right? For this given set of parameters, this code performs as I wanted it to. And for this other given set of parameters over here, this code performs how I wanted it to. By being able to do sort of static type checking before you run the code, you can take out whole dimensions, if you like, of that parameter space. You never have to worry now about the parameter space where this code, does it behave well if it gets ints or strings, right? Because you can now check before you run the code if it's getting the thing that it should be getting. So this is super useful, and this kind of goes hand in glove with the purity thing. So why I banged on so hard about purity as defined as you only care about your inputs and all you do is return outputs. Well, now you can type check those inputs and type check those outputs. So now you can really get meaningful guarantees that what your code is doing what you think it should do, right? That your code is behaving correctly. Because it has no internal state, it's not going off and affecting anything else. All it does is take in inputs, which you're checking, and return outputs, which you're checking. Really useful, okay? A very kind of useful guarantee to be able to get from Python. Next thing I want to discuss is laziness. So laziness is a really interesting concept in functional programming. And it's one that's almost impossible to kind of reproduce outside of a functional context. It actually, I would say, is impossible to reproduce outside of a functional context. But you can do some really nice kind of lazy type things in Python. And I'll kind of talk you through what I mean by that now. So laziness as a definition is fairly straightforward. In Python you've got this concept of an iterator, right? For character in string, for value in list, for key in dictionary, you can iterate over objects, okay? It has a really nice iterator protocol. And the notion here is that when you're dealing with laziness, you've got some kind of setup like this. Okay, so perhaps you've got an input. Okay, it's a very straightforward kind of idea, but you've got an input x, which is potentially infinite in domain. Okay, so x could be all the natural numbers, right? And what I want to do is I want to perform run some function over x. Okay, so do some function to all the natural numbers, and then I want to run some function over the output of that, and maybe select just one value. Okay, now dealing with potentially infinite inputs is a worrying thing, right? You haven't got infinite memory, you haven't got infinite compute, so you're not going to be able to do very much with it. But the notion of laziness is that the computation is not driven by the input, by the x here, which is potentially infinite in domain. The computation is driven by g, by the outer thing. So g tells f, I need you to compute a value because I need to check if that value is the one I want. And f says to x, okay, give me one value and I'll compute the thing on it and see if that's what g wanted. And then if it is, we stop. The computation terminates at that point and we do a finite amount of work. And if it's not, we go back to the start again and we say, okay, I need another value because that wasn't the one I wanted. And the process loops around like this, okay? So the notion of laziness is very straightforward here. G drives all of the computation, not the input, but the thing that's demanding output, okay? It asks for outputs and they're only computed on the fly as needed. So this is a really useful thing, and it's something that Python sort of provides through its generator interface. So generators are a super useful thing in Python, which have this kind of form, right? So this is a simple function or a generator called numbers. It takes in an input, okay, which will default to 0, and it returns an output, which is also an int, okay? So I'm type checking this, so I'm making sure that it does the thing it should do. And it just says while true, so long as true is true, give me back x, and then increase x by 1, okay? So I can then create an instance of this function or this generator called n, and I can call next on it, okay? So by, say, print next, and I get 0, and then it waits. It doesn't do anything. I say print next again, and it gives me 1, and it goes back and it waits. And this is exactly the same as the kind of example that I gave of g driving the computation, right? The print wants a value, the next goes off and gets a single value from this potentially infinite generator, hands it out to print returns it to the screen, and then we go back and we do the same thing again. It just waits for you to call the next value. All right, so this is a powerful tool that Python provides, which sort of mimics laziness in functional languages and provides us with some really useful ways of doing things then. So some really useful workflows can be kind of developed off the back of this. So as I say, n here is an infinite list of numbers, right? N is, so long as you keep calling next on it, it'll just keep giving you back bigger and bigger numbers. There's no end to n. And we can then kind of use the Iterators package, which is a super useful package, one of the best packages in Python for my money. And it provides a function called takewhile. And we can say, take from this potentially infinite list so long as some predicate is true. So we can do really nice, I'd say, infinite domain type calculations like this. So we can say, okay, this line here, odd nums, okay, using the soft brackets, we're using generator comprehensions rather than list comprehensions. So nothing gets evaluated when you use the soft brackets. So we say, okay, for x in numbers, okay, numbers is infinite, give me x so long as x mod 2 is 1, so long as the number is odd, okay? And then odd nums is an infinite list of all the odd numbers. At this point, no work has been done, nothing has been calculated. This is kind of a promise that if you ever ask me to, I'll give you all the odd numbers one by one, okay? Then we can do this next thing with numbers less than, okay? So this is another example of us kind of doing slicing over generators. We can say take from odd numbers so long as its predicate is true. The predicate is just some thing that I made up, evaluate some quadratic function, and if it's less than some value, then return true, otherwise return false. So long as its predicate is true, so long as the value is less than this threshold, then give me an odd number, right? So that's all the odd numbers less than, or where this predicate evaluates to true. Again, no work has been done at this point. This list is now finite, but we haven't actually computed anything, okay? It's a generator. And then we can call sum over this thing, and we can say sum of all the numbers less than this thing, and we get out 169. So all the computation is being driven here by the sum function. So this is a really useful workflow. This is quite an abstract example. I'll give you a more concrete one at the end. But this is a super useful workflow to have. The access to this kind of generator syntax lets you slice potentially infinite inputs. Okay, so let's say you were dealing with extraordinarily large inputs, as you often are in data science, right? You've got gigabytes of data on disk, and you want to be able to look through that data and find some answer. You can't read it all into memory, so what do? You write something that looks like this. Okay, this generator syntax will only evaluate what needs to be evaluated when it needs to be evaluated. So it will only read the file, for instance, line by line, and perform some kind of predicate over that line, one at a time. You could do this even with potentially infinite inputs, like say you're reading from a log file that's being live written to, right? That file, as I say, it's infinite. So long as the sensor is up, that file's going to keep getting data. But you can use this kind of generator syntax in Python to do a finite amount of work over that potentially infinite amount of input. I'll show some more concrete examples of that towards the end. So the next thing then is probably the most important, is higher order functions. So this is sort of the real bread and butter of where functional programming gets its power from. So what I've covered up to now is the notion that a function only takes in inputs and only returns outputs, and that's it. If you do that, then you can type check those outputs in a meaningful way and start to understand what your code is doing. And if you have the notion of laziness, you can start doing work that that sort of abstracts away from the data structure in some sense. You're not worrying about the data structure. The data structure is potentially infinite, but you can still do computation over it, which is nice. Now we're going to go to the idea of higher order functions, which is taking all of those little pieces and being able to compose them together, combine them in flexible ways. Okay, and this is where the real power of functional programming kind of comes in. Being able to do very flexible composition is where you get the value and get the power. So begin with a very simple example. So let's say we want to do something like this. This is a pretty common workflow, I guess. So we've got like a list full of names, right? Alice, Bob, and Eve. We want to capitalize the names. We have a for loop which goes over for name and names, capitalize the name, give it back to us, right? Cool. This is a pattern, I would say. This is a thing that everyone does all the time, right? You iterate over the values in an iterator and you apply a function to those values and then you capture the outputs into another iterator, into a list in this case. Okay? Very nice and very transparent. Wouldn't it be nice if we had a way of doing that automatically, if we didn't have to write all this boilerplate code to do this very simple thing that we do all the time? Well, we don't have to, right? And so this is kind of the pattern here encapsulated. We have data, which is comprised of values. We have some empty output. We iterate through the values in data. We append to the output a function applied to the value. That's a pattern. I'm sure you're all ahead of me on this and you know where I'm going with it, but wouldn't it be great if we had this loop append thing, okay? Loop and append function will be really useful. The thing about loop and append function is that it's not like other functions we've seen up to now. It needs to take a function as an input because there are two variables in that code block that I showed you before. There's the data which it works on and there's the function which it applies. And again, I'm sure you're all ahead of me. This exists and it's called map, right? It's a thing that everyone uses all the time, but that's what it is under the shell. Right? The notion of map is that it's this pattern that we've got that we do all the time. Apply a function across all the values inside of some list. So that's we abstract that away and we call it map. So we can map, capitalize onto Alice, Bob, and Eve, and we get this nice output. You'll notice that I'm calling list on this thing because as of Python 3, map returns a generator by default. So map can operate over, again, infinite domains because it doesn't actually ever do an evaluation until you compel it to, right? So at this point, like map string capitalize Alice, Bob, Eve won't evaluate until I call list on it, at which point it says, okay, I'll go away and calculate that thing you asked me to now. So that's laziness in there as well. So this is really useful and kind of hammer home the point that I was going at there. This is a slightly different kind of function to what we've seen before because this function takes functions as an input, and that is the definition of a higher order function, a function that consumes functions. There are lots of these in Python. This is another pattern that you do all the time, I guess, filtering. So you want to go through all the values in a list, and if some predicate evaluates true on that value, then keep the value, otherwise throw it away, right? Thing you do all the time. Again, it has a name, it's called filter, right? So filter anywhere x is greater than 10 from this list, gives you back to places where it's greater than 10. Again, it's a generator, I have to call list on it if I want to get the values rather than just getting a promise of the values. Cool, so there are two very useful ones. Another one that's slightly unusual, but I think is extraordinarily useful, no longer exists, unfortunately, in the Python standard library and has been moved into func-tools because apparently Guido van Rossum finds it really confusing. But it's called reduce, and this is its signature. So it's got a slightly unusual signature. So what it does is it's G here. So reduce is some function G which consumes a function, an iterator, and an initial value, and then it does this kind of weird nesting thing. So it'll apply the function to two values and then use that as one of the arguments of the function applied to another value and the output of that, and then use that as an argument with this initial value. So that's kind of weird, maybe slightly hard to parse signature of this kind of embedded or almost recursive-like function calling thing. Okay, this is why I guess Guido van Rossum doesn't like it, because it looks a bit gross when you write it out like that. But what it does is quite straightforward. Okay, and for an example of it is here. So again, it lives in func-tools now, unfortunately. But you can go into func-tools and import reduce, and you can go into operator and import add. So all operator is it's the plus sign, but written as a function, right? So add 1, 2 is the same thing as 1 plus 2. Okay, and we can reduce add across this list starting with 0. We don't actually need to say 0 here because that third argument defaults to 0, but we will. So reduce add onto this reduces, if you like, into just a sum operation. What we're doing is we're summing up all the values in that list. So we're applying add using that kind of recursive signature. We add two of the values together, we get an output, and then we use that as an input into another add operation where we take that summed value and some other thing to it, and we keep doing this recursively until we exhaust the list. So we can add everything together and we can get a sum, which is very nice, a useful thing to be able to do. We can also do factorials in exactly the same way. So we apply the multiplication function across this same thing, this time starting at 1, otherwise you'll get nothing. And this is how you can do factorial in Python. This is actually probably the fastest way to do factorial in Python, both in terms of keystrokes and also in terms of execution. This is a very fast way to do it. So cool, that's very useful. We can combine these things together and we can combine them with map as well. So one thing that kind of a lot of data scientists in the room will be familiar with is the notion of the map-reduce paradigm. This is where the map-reduce paradigm comes from and gets its name. You can combine map and reduce together to do workflows that look like this. So this is computing a dot product, okay? So we map multiplication across these two lists. So we, in other words, pair off the the values and multiply them by one another. So 1 by 2, 2 by 3, 3 by 4, 4 by 5. Probably should have picked better numbers. That was maybe not clear. And then I do a reduction across all of that. I reduce all of that with add, so I sum up the output. That's a dot product. And why this is a super useful thing in data science in general is the map-reduce paradigm is inherently parallelizable, right? So those map operations can be done on different cores. They don't need to be done near one another because they never talk to one another, right? The multiplication of 1 by 2 and 2 by 3, they don't need to know, they know nothing about one another. They don't rely on the same input. So you can map those off onto a bunch of cores, and then the reduction operation goes around all those cores and collects the answers at the end and brings them together using some kind of function, okay? That's why it's a really useful thing, and that's why you see it everywhere. So that's why it's worth mentioning. It's another higher order function that kind of makes for a useful way of gluing together these small, simple functions. Another one that I'm going to go and talk about a little bit is called currying. So this is named after Haskell Curry. So the programming language Haskell was his first name, and currying is after his second name. And currying is a simple enough thing. It takes in a function of multiple arguments and returns a function that can be called on the arguments individually. So this is its signature. So let's say we have a function which takes 3 arguments, x, y, and z. We get back a function which will take in x, and then return another function which takes in 1 argument called y, and that will return another function which takes in 1 argument called z. Okay, so it seems like a kind of weird thing to do. Maybe you don't, but you can think of examples of where this might be useful. Maybe you don't know all the arguments at one time, and you want to create a new version of the function that sort of encapsulates some of its arguments. This is something that would be very common, I guess, if you're thinking about parallel between this and kind of more general concepts in Python. This might be something like an object, right? You can create a Python-style object, like almost like a class, where you've got some function that has data embedded in it, right? When you curry it with this first argument, you get back a function that in some sense has data contained inside of it. It knows what x was set to, right? So this is a useful thing to be able to do. I'll give you a brief example of it. So this lives in my definite favorite Python library called Tools, which is just wonderful. I'd really recommend it. It's a whole bunch of functional programming tools, all written in pure Python, all providing lovely generator syntax for laziness and all the rest. And it's just a really useful thing. I'll give you some more examples a bit later. But we can take curry from Tools. We have this nice function here. It takes in 3 arguments called add and scale. It takes in 3 ints. It adds the first 2 and it multiplies by the third. We can then curry add and scale to get back a new version of add and scale. So calling curry on add and scale gives back a new function, and that function has this new signature, right? So rather than taking in x, y, z, you see I'm calling it here using x, then I call it again using y, then I call it again using z, okay? Again, this might not seem like a useful thing to be able to do at the moment. I will give an example at the end of how kind of you can use this in a workflow. But that's the idea of currying, right? I hope that's clear, that we kind of take a function of multiple arguments and turn it into a sequence of functions of 1 argument. And the final one that I want to discuss, because I'm sure you're all getting tired of higher order functions, is called composition. And this is probably the most straightforward of all. You've got this 2 functions, f and g, that you're calling on some input x. Wouldn't it be great if you could combine them together and call them by one name? So you have this idea of composition. G.f becomes a new function that does f first and then does g. Straightforward, very simple idea. We can use it. Again, it lives in tools. Go to tools, import compose. We have an add and a multiply. Just kind of define these here for clarity. Add takes in 2 ints, adds them together. Multiply does the same, multiplies. I can curry the multiplication by saying multiply by 2. So mul2 here is now a new function that will take in 1 input and multiply it by 2. I can then do add and mul2 by composing the multiplication by 2 with the addition function. I now have a function that takes in 2 arguments. When you give them in, it adds the 2 together and multiplies them by 2. So that's kind of combining the currying idea with the composition idea. It maybe seems abstract or like a thing you wouldn't ever need to do, but bear with me and I'll give you an example that hopefully justifies why this. I suppose it's an unusual type of syntax to see in Python. It doesn't kind of gel with the way you conceive of putting functions together in the language, but I think it provides you with an awful lot of flexibility, and you can kind of see how I'm getting to the notion of composability being at the core of this, right? What's useful here is that I can combine functions together in a more flexible way than I otherwise could, and that's where I get power from. So I've kind of gone through all the examples that I want to discuss, the purity, static analysis, laziness, and the higher order functions. And now I want to give you an example just to sum up of kind of how you can put all this together into a single workflow that I think leads to some, maybe there are arguments to be had, but I think some very readable and some very clear code that is a little better than the other example. So let's jump into the example. So the example that I've got is I've taken all of the lyrics of every song that has charted on the Billboard Top 100 in the US since the 50s. So there's loads of songs here. I don't think I know any of these. None of those ring a bell for me. Oh, Wannabe is there. It's a good song. But that's about all I've got. So yeah, so it's a whole bunch of songs. There's like 1,000 files in that directory, or maybe a couple more, I can't recall. A lot of files. And they all contain just the lyrics. Oh, Nothing Compares to You is there as well. Okay. Sorry, that just seems fitting to be at an Irish conference and have that appear. Cool. Okay, so we've got a big directory that contains loads of files, and each one of those files contains loads of lines. 5 minutes, cool. We're going to go through those, and we're going to do some analysis to it, right? So one thing we might want to do is might want to count the words or the appearances of words in this thing, right? Get some kind of mapping of words to how many times that word appears. We can get the most popular word then, right? So we do this in an imperative way with this word count imp function. So it's word count imperative. It takes in a directory as input, and it's a very simple function, and it's not a bad function. I would say that I wrote this function, so I suppose I would be biased in favor of it, but it's fine. It does what it needs to do. It generates a default dictionary, which takes in ints. For those of you who don't know, a default dictionary is just a dictionary, which if it doesn't have that key in it, will just give you back a default answer. In this case, it'll give you back 0. That's handy. I iterate over all the files in the directory, then I iterate over all the lines in all the files. For each line, I do a split. For each line, I do a lower, and I take out all the punctuation. Then for each word in the line, which I've split on spaces, I insert them into a dictionary. I increase a counter by 1 for that word. Okay. Then at the end, I do a little bit of dictionary stuff where I do a dictionary comprehension that says if the length of the word is greater than or equal to 4, keep the word, otherwise drop it. I don't want any short words in here. Okay. It's a fine piece of code. It does reasonable things. It's a bit gross that it's got like 3 nested for loops in it, and it's obviously impure because it's doing this overwrite to the line function, or to the line variable rather. We don't like overwrites in functional programming because they generate confusion. So line starts off being a string of characters, then I turn it into a list, and then I iterate over that list and do something to each of the objects in it, which is a slightly gross thing to do in a place where you can get a bug from. But it's fair enough, and we do this, and we can sort the words by how many times they appear, and we see the most common ones are like, that, your love, don't know, like, just, with, baby, what. Cool, great. So that's a useful thing to be able to do, right? But we can take this kind of workflow and we can do something maybe a little cleaner with it in functional programming. So I want to talk you through an example of doing the very same thing now in a functional way that I think is maybe a little easier on the eye and easier to understand. It sort of abstracts in some sense what we're doing. We're going to go to tools, and we're going to go to its curried submodule. So it has a submodule called curried, which is just the curried version of everything that's in it. And we're going to import these few things. Okay, I'll talk to you about what they are in a moment. We're going to define 3 simple functions, 3 very small functions, which we're doing type checking on. We're going to do a stem function, which takes a word, a string, lowercases it, and removes its punctuation. We're then going to do a drop word function, which just returns a boolean. Is the word longer than 4? Yes, give me a true, otherwise give me a false. Then we're going to do this frequencies function, which takes in a list and returns a dictionary, and all it does is it goes through the items in that list, and it inserts them into a dictionary where the key is the item, and the value is how many times the item appeared in the list. Okay, we don't actually need to do this because this frequencies function in tools does it for us, but I'm doing it here for the sake of clarity and for the sake of making kind of very explicit what I'm doing. And then we just define this workflow. Okay, and this is the whole body of the code. The workflow is glob. So glob goes and gets all the names of the files in this directory. Mapcat does a map function, so it maps across all these inputs and then concatenates all the outputs into one big long list. Okay, that's all mapcat does. It's coming from tools. I say mapcat open onto this. So mapcat open onto all of the files in this directory, which means open them all and concatenate them all into one big long file effectively. Then do mapcat string.split. Split all the lines up on space and concatenate all that together into one big list again. Then do a map of stem across it. So take my stem function and run that across all the words in this now, this big list of words. Then take my frequencies function, map that across all those words. Okay, so now I've got stemmed words, I've computed their frequencies, and then do this key filter thing, which is coming from tools, which just says filter this dictionary, because at this point this thing is going to be a dictionary, and filter it using the drop word function. Okay, so anywhere this drop word function evaluates to true, keep it, otherwise drop it out. Okay. I think that's a very clean thing to do. I think that the kind of 4 lines there sum up in a very declarative way what we're trying to do. We haven't had to write the code down. We haven't had to say for I in line or for, we have no looping. We have no constructs like that. We've taken all that and abstracted it away into these map functions. We've combined those map functions together here at the bottom using this compose. So this is just a tuple full of functions. We then compose all those functions together into one function. And this is kind of a different way of defining a function that you don't often see in Python. And then we compute the words across it doing exactly the same thing. It takes in a directory as an input and it applies this series of clarity defined steps. Cool, and that's what it does. It does exactly the same thing as the previous function, but for my money it's an awful lot clearer. It's an awful lot less prone to bugs. There are very few places you can go wrong in writing this. There's a lot of places you can go wrong in writing triply nested for loops that contain like overwrites of things that were strings and now were lists and stuff like that. But there are very few places you can go wrong here, so long as you kind of understand the abstractions that you're applying. And then you get the very same thing out. So to kind of finalize, one thing that I did with this is I took also the lyrics of all Bob Dylan songs and I ran this over both of those things just so it's nice to finish with a result. I took both of those dictionaries, so the dictionary of word occurrences in Billboard Top 100 songs, the dictionary of word occurrences in Bob Dylan songs. I mapped those two things together, subtracting the most common words from Billboard from Bob Dylan, so find the words that are most Bob Dylan and the words that are most top 50 songs or top 100 songs. And the words that are most Dylan look like this, and the words that are most Billboard look like that. So it's nice to finish on a result from data. Things like poor, train, hard, lonesome come from Bob Dylan songs. Things like baby, wanna, etc., come from top 100 songs more frequently. So that's just a very brief example, I think, of kind of a workflow in Python that you can put together using these functional principles that leads to code that is, for my money at least, clearer, more readable, and as a result of this kind of composition of individual modules, more powerful. I'll leave it at that point because I think I've taken enough of your time to get on my hobby horse about functional programming, and leave up my contact info if you want to get in touch, or find these slides. They're on GitHub at Neal-o-or. It's all in one big Jupyter notebook, all the code runs, and it comes with an awful lot of other examples that I did in kind of other versions of the talk and decided were not particularly illuminating or useful, but you can feel free to dig into that code and take a look. So I'll leave it there and take any questions you might have.
I just wanted to ask if tools is part of the Python standard library or it's an external module?
It's not, it's an external module. Yeah, it's written by Matthew Rockland, the guy who wrote Dask.
Okay,
yeah.
Thanks.
Anyone else? No? It was either very good or very bad in that case.
I have a question.
Yeah.
Can you tell me why compose expects the arguments in reverse order?
Yeah, that's a good question. So there's two options in tools. You've got pipe and compose, and pipe works the way Unix pipes work, so you read them from left to right, and compose works the other way around, here from right to left. I think it's like a mathematical notation thing. When you do composition of functions in maths, they apply in the order. The one that's closest to the argument gets applied first, and the next one, then the next one, then the next one. So it's just a syntactic thing.
If I want to explicitly run the chunk 24 in parallel, is there a keyword that I can use, or will the tool...
Sorry, to do parallelizable, which example do you mean?
Chunk 24.
Sorry, I can't hear exactly what you're saying, but this one here, you want to use this? Yeah, so tools itself provides parallelizable functionality, so you can do it based on that. All their functions are kind of natively parallelizable, so yeah, you can take advantage of lots of courses using that.
Thank you.
That's good. Cool. All right. Thanks a lot, folks. A lot of fun.